nice slides to show anyway, so I thought I'm going to talk a little bit also. If I can, okay. So what is the reason why we'd be interested in reaction theory to begin with, right? So there are a couple of main reasons, at least that I can think of. The first of the many reasons is that nuclear physics and nuclear reactions in particular are at the basis of some phenomenon that we'd like to understand pretty well, just for the sake of societal applications and also for applications in other scientific topics, right? So we need to understand what goes on when different nuclear species collide in order to have a good grasp of important topics like fusion, fission, for the sake of producing energy, also nuclear medicine, and as I said before, also some other scientific topics like nuclear astrophysics. So this is one of the reasons, right, why we want to understand exactly what is going on when nuclear species collide. But also, and that concerns much more what's going on here at EFRIB, if one is able to control nuclear reactions and to actually to carefully design experimental energies and the species that are colliding, we might hope actually is one of the best ways that we have at our disposal, the best experimental way, to ask or to probe our understanding of the structure of nuclei, right? So nuclear reactions is not only important for societal applications and other scientific topics, but it's also one of the best experimental tools that we have at our disposal. And I have here one of my favorite examples on how that can be done. Again, what one needs is to be able to prepare with a well-defined energy, a specific beam. One also needs to be able to have a target, which is going to collide with our beam. And one, in a well-designed experiment, one might be able to learn something about some specific aspect of nuclear structure. In this example here, one might want to learn something about the single particle content of the spectrum of nuclei, in this case, of T120. So this is a little example in which we have a deuteron beam. This is a direct kinematics experiment. T120 is stable, so we can do that. Probably that would not fly with the EFRIB pack, but you can do that elsewhere. And you shoot your deuteron into your target, T120, and you detect the outgoing proton. So this is a very typical experiment. You have a beam, you have a target, and you detect the resulting, the product of the reaction as a function of the energy of the proton in this case, and the deflection angle with respect to the incident beam. So what are the observables that we are interested in order to address our knowledge of the single particle spectrum of T120? One, well, there is first the energy of the proton, as I said, and the different energies that one can detect are associated with, of course, the discrete states of T121. You can start to draw like the scheme of the spectrum. One can draw that energy, that detection energy, right, as a function of the number of detected protons, right? And we see different peaks that again are associated with a different state. And one can also actually look at the absolute value, so the number of protons, right, per unit time that are detected that is connected to the single particle, the cross-section and the single particle content of that particular state. This is an important observable. Of course, the position, which is going to give you the energy. And also, if one is actually probing the continuum, those states will have a sizable width, which is going to be essentially the particle escape width. And we will see also that the width is also an interesting observable that we can compare with our understanding of nuclear structure. But we can also detect, as I said before, the deflection angle of the proton with respect to the incident beam. And it can be shown actually quite easily that the actual shape, the diffraction pattern that one can observe when one plots the cross-section of the fraction of the angle is a very clear signature of the angular momentum content of the states. Okay, so this is an example on how this particular reaction, which is a transfer reaction, can be used in order to learn something about the structure of T121. In order to take full advantage, of course, of those experiments, one needs to understand what is going on, understand the process, and being able to actually get some quantitative account of what is going on in terms of the structure and the reaction aspect of the process. So one of the challenges that we have to face, even if we are only concerned about nuclear physics, nuclear physics or nuclei are rich enough so that you have to care about very different characteristic features of, for example, the spectrum of a particular nucleus. So I have drawn here, right, as a function of the excitation energy, the spectrum of a typical nucleus. This is an invented nucleus that I'm going to call fictitium 30, for example, okay? But it is very representative of what's going on in a real nucleus. So if one plots, as I said, the cross-section of a particular reaction, no? Say that we're looking at elastic scattering or inelastic scattering, it doesn't matter. Something is going on, and we observe the probability of that something going on as a function of the excitation energy. And here I have a vertical representation of the spectrum. So of course, the nucleus is a quantum system. So we have, in general, the nucleus is bound, a discrete spectrum to begin with. So this is what we have as we move away from the ground state, and that shows up as very narrow peaks in the spectrum as a function of the cross section. And at some point, so those peaks are getting closer and closer together. So the density of level is rising. And at some point, we will cross the first particle emission threshold. So above this excitation energy, the system is able to emit particles. So it's not bound anymore. And as a result of that phenomenon, right, so the peaks that were narrow start acquiring some width, sizable width. They're getting more and more together. You have more and more on there. At some point, they start to overlap. And if we get like even higher in energy, those peaks sort of merge all together. We're not able to distinguish them anymore, even physically, without taking into account the experimental resolution. They are one on top of the other, but we still have some structure, right? Some general structure that manifests themselves typically in the form of giant, what we call like giant resonances. So if we want to do a good job describing reactions, we should be able to address, right, the entirety of the spectrum, because each region actually is interesting for its own sake, as I said before, both for applications and also for as an experimental tool and to enhance our understanding of nuclei. So how do we do that? So we do what human beings do when they try to understand nature, right? So you narrow down a specific regime that you're interested in, and you devise a particular formalism or a particular theory that is particularly well suited for the specific regime. And, as it's often the case, the particular formalism theory that is good to actually describe what is going on for a particular regime, for example, here for bound state, we have direct reactions, is not necessarily very useful when we address a different regime. So here, we can see that if we want to describe what is going on typically when resonances start getting pretty numerous, but they're still separated, instead of using direct reaction theory, we will use aromatic theory. I'm not going to go into details. What I want to highlight, the only thing that I want to highlight is the fact that we are going to need different theory. Of course, nature doesn't care that you're looking here instead of there. There is just one quantum mechanics that is applicable everywhere. But human beings, again, have to compromise. And if we go even higher in energy, and we are looking at that part of the spectrum where everything overlaps, where we are not able anymore to distinguish specific individual peaks, we recur to a statistical description of the nucleus, right? And to what we call the Hauser-Selke theory. So it would be interesting, right, to try to see, because again, what happens typically in physics is that when those regimes are very well distinguished, when we know very well to which one we are looking at, it's, the different theories work very well. But of course, at some point, we will have to come to terms with the fact that some systems or some regimes will sort of lie in between. So it's still interesting to wonder whether we can treat everything on the same footing, or at least to draw bridges between those different regimes. And therefore, we can address the problem of some kind of unification of all those regimes and ways of behavior in the following sense. So this is my personal wish list. Of course, it's not unique, but I would say that would be interesting to be able to address at the same time, or in a transparent way, both bound states and the continuum, right? Those spikes and the resonances. But also what we call the direct and the compound reactions. Compound reactions are the ones that happen in the statistical regime that I talked about earlier, right? And of course, if we want to understand and to address our knowledge of structure, it is very important to be able to write down our cross-section, the results of our experiments, in terms of the structure, the underlying structure that defines the particular nucleus that we are describing. And in this sense, we want to, if you want, unify structure and reaction. But also, an important aspect of science, okay, so this is not supposed to be like that, right? This U is uncertainty, this Q is quantification, and everything is supposed to be in this little circle. Okay, so we also would like to address the quality of our prediction and compare it to as a function of the quality and the resolution of the experiment. So we want to be able to do some uncertainty quantification. I'm not going to talk about this particular issue in this talk, but this is very important. And people here, like Filomena, for example, have been pioneering, right, the rigorous uncertainty quantification applied to nuclear reactions. I just want to say that it's an important thing. I'm not going to talk about that. So let's start from the beginning, right? So I'm going to ignore the guidelines of the talk that asked me to not put any equations. I hope you will forgive me. I'm just hoping that this is going to be more pedagogical than confusing. There are going to be few equations here. So this is the easiest scattering state that we can think of, where two structureless bodies collide. They interact through a potential, right? That can be described in principle in a coordinate space. In principle, it's going to be non-local. It's going to be energy dependent. It can be pretty complex. We'll go there later. But we can describe, if we want to have some hope of describing what is going to go on here, we have to describe the interaction between those two bodies, right? So, okay. So, okay. So one way to write down, of course, this is quantum mechanics. So all the knowledge that we might hope to have about this two-body system is through the wave function, the wave function of the relative motion between those two guys. This is the wave function, right? This is going to be connected, of course, with whatever observable we want to address. And an interesting way of writing down this wave function is through the Liebman-Schwinger equation. So this is the Liebman-Schwinger equation, and it has a pretty suggestive, I would say, interpretation. So this is the unperturbed wave. This is the incoming wave. This is a plane wave. This is what X and A would feel if there would be no interaction between them. And as a result of the interaction process, of the scattering process, that plane wave is going to be modified by this operator, right? This is the Green's function. This is the potential. More on this later. But just think of that Liebman-Schwinger equation of a way of translating the result of the process in terms of this operator. This operator transforms that incident wave into a scattered wave, right? And this is what we want to observe. This is a pretty compact way of writing everything down. This is the potential. And that object here, that ominous Green's function, is just the inverse of the Hamiltonian that includes the interaction potential, okay? So once we have the wave function, of course, we have everything we need. In particular, we can calculate the reaction cross-section, right, as the matrix element, the average value of the imaginary part of the optical potential. I'm not expecting that you guys are going to, yes?
The imaginary part?
Yeah. Yeah, so the imaginary part account for all the flux that is going away from the
reaction cross-section. Yeah.
So that is
Okay.
the reaction cross-section, yeah.
Okay, very good.
This is a way of writing it. There are many other ways, but this is going to be useful for my little story, right? So we have everything we need, right? Once we have the wave function, this is not a surprise. But now, okay, this is two-body scattering. This is very interesting. This is very useful, but we want to go a little bit further and to expand the scope to three-body scattering. Okay, so now instead of having two bodies that are colliding, we have three. Right? Let's assume that our problem is amenable to an effective three-body problem in which we have a projectile that is effectively composed of two clusters, right? That one can identify. Those two clusters interact also via two-body interaction, which is this one, VBX, and everything interacts together. I'm not taking into account here the existence of three-body forces, so bear with me, I'm not going to talk about that. So apart from this is a pretty general way of stating the problem, right? Those potentials are of similar nature of the two-body potential that I was talking about before. So this is still too complicated problem for a lazy guy like me. So we are going to do some approximation. We are going to do an approximation that is going to decouple that effective three-body problem into the product, if you want, of two-body problems. And the way we are going to do that is by using the spectator approximation. So we are going to simplify the description of this little cluster B, so the interaction of that little cluster B with this two-body system by just an effective interaction U that is going to be simple, that we're going to fit to some experimental observables in such a way that we will see, not surprisingly, that the movement of that cluster B is going to decouple from what is going on here, okay? So this is an approximation. It has, of course, its range of validity, but it is very useful and it applies very well in many cases of interest, so I'm not going to enter into the details. So then the Liebman-Schwinger equation that we had before gets a little bit more complicated, right? But not too much, We still have an incident wave, which is a plane wave for the relative motion of those two guys, and the intrinsic ground state of this projectile here. So what we have here is a description of this little A cluster just traveling without being disturbed in free space, right? This is the internal structure, this is a plane wave, and this is the scattered wave. The scattered wave, as before, we have an operator that takes care of the evolution, which is the Green's function, and this is the potential. And the potential, again, is simplified with the sum of two-body potential, one for that motion and another one for the little cluster B. This is the essential simplification, and also the fact that this sort of evolution operator, the operator that is going to transform our free wave into a scattered wave, is going to factor in two terms. So this is the simplification. Okay. Yeah. Okay. This is just a projector onto the state of the observed B particle. This is the guy that we observe in our detector. If you think about the DP reaction I was describing before, that would be the proton, but this is more general, right? And this is just a projector onto the observed state. This is the same, and this is very important, Green's function that would describe the isolated two-body problem, right? It's exactly the same. It includes the potential that describes the two-body motion. Okay, function. Factorized propagator, as I said before, this is the essence of the approximation when we can actually describe the three-body problem as a product of two-body motions. Okay. Now we project onto the final observed state, right? This is the process of observation, and once we do that, okay, we have a funny term, the Hussein-McCoy. We don't care about that right now. But the point is that we have what we want, which is the possibility of describing the cross-section, the reaction cross-section, for observing this little guy here, the B, which is going to be sort of the messenger that is going to bring to our detector the information about what was going on here, as a function of all the ingredients that we have here, right? And it's very similar, right? We have the imaginary part of the optical potential, except now the wave function we have to factor over is this a little bit more complicated wave function that we have calculated with this a little bit more sophisticated version, if you want, of the Liebman-Schwinger equation. So that, by the way, so this is something that that little formalism was developed when I came here for the first time with along with Filomena and Ian in Illinois, right? Yeah.
So this optical potential is between the B, right? So
This one
yes,
is the optical potential. So the potential, I haven't talked about optical potential yet, but it's, so you're spoiling my suspense. So this is the interaction between those two guys. This is very important, right? So this is going to be useful in a situation in which we hope to learn something about that two-body problem, those two guys here, by observing this guy here, okay? So it's important that we are able to write the cross-section in terms of the structure ingredient that address the compound, the composite structure, if you want, of those two bodies, X and A. So this is the motivation of this little gymnastic that we did here. So at the end, fine. But of course, this is a three-body problem. I was talking about a two-body problem. Nuclei are more complicated than that. So nuclei have internal structure. So that little x and that big A that was approximated as, structureless body actually has some internal structure chi, which account for, if you want, for all the coordinates and spin of the composing nucleons, right? So this is a little bit of a more general way of writing my Liebman-Schwinger equation, okay? So now it is more general because now I'm allowing the projectile and the target to have some internal structure, right? And therefore you see that those G and those V now are bold-faced because they are many body operators and not two-body operators, right? So it's much more complicated, but fear not, because once we project on the observed state, let's say that we observe the ground state of the target and the B particle, the big laser flying away at a particular angle, then this projection procedure is going to simplify those many body operators, at least I hope, and we will have an effective two-body operator, which is going to be called the optical potential, and this is going to be the single particle function. This is complicated, but I will get to it later. The point is that those guys are now, after the projection, single particle operator, right? That we can deal with. But now, okay, I wanted to say something about something that is very often said, and I have mentioned that. People talk very often, this is very fashionable nowadays, about the unification of structure and reaction, right? So a very legitimate question would be, what is structure and what is reaction? So this is my own personal, approach to that. So how can we tell? This is just semantics at some point. We might not worry about that, but I think it's interesting to wonder, right? What are the things that a structure theorist can calculate, and where does the reaction come about? So this is our function, everything is blended together. I would say, personally, that whatever goes to zero as we get far away from the object that we're describing can be called structure. A structured object is something that is confined in space and dies off as we get farther and farther away. Those are the ground state of the target, the ground state of the projectile, and that optical potential, which has a limited range. We're talking about strong interaction. And all of the things that actually has an oscillatory boundary condition, so they actually never die away, so they are present like everywhere in space, is what I will call a reaction object, if you want. So in this context, the unification of structure and reaction would mean simply that all those guys are calculated somehow within the same framework, right? Or on the same footing, if you want. You can do that. I'm going to show a way of doing that. And that can be done making use, and I think that this is also important, of your framework many-body theory of choice, right? So I have listed here some popular ones. You can calculate it ab initio with some effective field theory. You can use a beyond mean field description with a G-matrix interaction between nucleus and so on and so forth. It doesn't matter as soon as one preserves this, that whatever you use for the structure calculation of that optical potential, then the reaction part, which is going to be embodied in the Leibniz function, is going to be the inverse of that particular optical potentials that you have calculated with a specific framework. If you do that, you are guaranteed that whatever the result of your calculation in terms of the reaction cross-section is not, so if it's wrong, it's not your fault as a reaction theorist, it is the structure theorist's fault, right? That hasn't calculated that correctly. So of course that makes me very happy. So I'm going to, this is not necessarily new, right? We have not invented everything. Actually, people have been calculating reactions for a long time, and there is a very popular approximation to calculate reactions, this total wave bond approximation, that is based on essentially, the Fermi golden rule, if you want, right? So you have an initial state, you have a final state, an interaction that couples you from the initial to the final state, And the cross-section, the probability for that process to happen is very natural in quantum mechanics expressed at the modulus square of that matrix element here. This is essentially the basis of this third wave-one approximation. What we just described is a little bit more complicated, but we already saw, right, how we can obtain that cross-section also as a function of that matrix element of the imaginary part of the optical potential with that scatter wave. Okay, so what are the differences? What are the possible advantages of that GFT, Green's function transfer, that we have just described with respect to the good old way of calculating reactions? Well, to begin with, so this applies very naturally to the description of what is going on when you populate well-defined individual states, because this is a matrix element that is only defined if you can define the final set that you're populating, right? This is a discrete in nature object, while that wave function that I have calculated, the scatter wave function, is parameterized by the continuous energy. It's a continuous function of the energy. So you can actually describe what is going on as a function, as a continuous function of the energy, which is, and also, by the way, it is very important that, so everything went a little bit wrong here, but the Green's function is a normalized object, right? The Green's function, right, includes in its belly the actual modulus of the state that you're looking at. Okay, so that wave, so that the absolute value of the cross-section need not to be renormalized by what people call like the spectroscopic factor, right, which is something that is extracted from experiment. And when you mention it like in a nuclear physics conference, all hell breaks loose. So if you want to stay safe, right, it's much better to not talk about spectroscopic factor and be able to say, well, the absolute value of the cross-section that I'm calculating, again, is the fault of the structure theorist that gave me that particular Green's function, okay? So you don't need to renormalize with spectroscopic factor. And also I would say that even though there are ways to treat the continuum within the DWBA, people have been doing that and they do it very well, let's just say that it's a little bit harder and less natural than within that formalism, because what I said before, the energy is a continuous parameter, and there is not any particular problem in describing what is going on in the continuum. What is going on in the continuum is particularly important in a place like EFRI, because you guys care about exotic nuclei, sometimes light nuclei, where there is a lot of interesting structure going on beyond the particle emission threshold that manifests itself in terms of resonances and so forth. So that is very nice to have that. And again, I'm just highlighting here the consistency between structure and reactions, okay, which is embodied in that connection between the Green's function, which is the, let's say, the reaction part of the description, and the optical potential. Yeah?
What is your T here?
Oh, the kinetic energy.
For the microscope kinetic energy, or is the cluster kinetic?
This is the two-body relative kinetic energy. Yeah. Two-body, like with our classes X and A, is just the kinetic energy between those two guys. Yeah. Okay. Well, all of that was also introduced in order to make the point that a particularly flexible and versatile way of embodying that connection between structure and reaction is through the optical potentials, through that single particle object that was obtained after projection onto the ground state of the target, right, of the many-body interaction. Why? Because as I said before, if you invert the Hamiltonian, where that optical potential is involved, you have the reaction aspect. And this is the structure aspect. So the optical potential is sort of the structure part of it all. We would like to be able to compute it. I'm not a structure theorist, but I care about, structure theorists being able to calculate it. And a possible, well, I'm going to skip through that. So this is just to say that the optical potential comes about after what some people call an optical reduction. And the whole thing has to do with that many-body Hamiltonian. I'm missing here the T because everything is going a little bit wrong. But that projection procedure allows you to project an infinite matrix into an effective single particle object. So this is what we need to learn how to do. I'm going to skip all that because everything went wrong after the projection from PowerPoint to the PDF.
You go back and forth, it might show.
Well, that's fine. I'm just going to talk, right? So this is just very schematically what you need to do. This is the final optical potential. The final optical potential is composed by a sort of mean field bulk account of the interaction, plus some account of the virtual excitation of all the internal degrees of freedom of your target. This is the hard part. You have to account for the fact that the two colliding species have an internal structure, and the states of that internal structure can be excited during this collision, and the account of those processes, real or virtual, actually gives you the optical potential. I'm going to go a little bit faster here because I want to be able to say everything. Okay, so this is just a mathematical way of writing down what one can barely see here, but writing down what you need to do. And the only thing that I'm interested in is for you like to remember that again, I have a sort of a static energy independent, like sort of mean field contribution, and then that complicated thing account for the virtual excitation of the internal degrees of freedom, and we need that famous Green's function again in order to describe that polarization part, okay? So I said before, one can choose different structure inputs in order to describe that optical potential and then the Green's function and get the reaction observable. One of them that we did with Gregory back when he was in Livermore with me. So we used the shell model, right? So we addressed the problem of describing the scattering of a neutron of a magnesium-24 target by describing the structure with the shell model and applying our little prescription to see how it works. If you do a shell model calculation of magnesium-25, which is the composite system that you get if you shoot neutron magnesium-24, you get a long list of states, about 600 states if you want to go up to about 15 MeV. Each state has its energy, its angular momentum, its parity, and the actual overlap, right, of the particular state of magnesium-25 with magnesium-24, which is the spectroscopic factor. If you have a shell model specialist in the team, it's much better. In this case, it was Kostas Kravaris who did that calculation, and he gave us this long list. So once we have that list, okay, we can actually explicitly do this sum. I'm going to skip some details because I'm running a little bit late. Okay, so the couplings, we want to do that better because now they're very simple, but we have to address the couplings of each of the ground state of magnesium-24, which one of the virtually populated states. And by running this little self-consistent scheme in which we make sure that the optical potential that we are calculating, for which we need the Green's function, actually gives rise to the Green's function that we will calculate with the optical potential, you get both the optical potential and the Green's function, which is, as I motivated before, everything we need. Does it work? Well, it's non-local, it's energy dependent, it's complex, and it's also pretty nice, right? This is just a mandatory nice picture. But of course, we're interested to see whether it works. I'm going to go a little bit fast here. Everything converges, and it compares pretty well to both data and what is calculated with a phenomenological optical potential. One can do a description also of that neutron plus magnesium-24 in terms of some optical potential that has just been fit to data, right? And the result is not perfect, okay? So there is also improvement to make. Gregor and myself have some ideas about how to do that, but it clearly goes in the right direction, right? So it seems that it's not too bad, right? But this is two bodies. Now we want to apply what we said about three bodies. So we are going to look here about DP reaction. Here, our three bodies are going to be the neutron and the proton of the neutron that we're going to shoot on our target, and the remaining third body is going to be the target. Okay. Well, this is something that we did during an ICNP workshop here at MSU. We got together some of the people that were working on that. We benchmarked our different approaches, and we described, for example, in this particular outlook, like the resulting paper, a DP reaction on different isotopes of calcium. And this is typically what you get with the Green's function transfer. You can get the cross-section for the population of different angular momenta in the residual nucleus, calcium-41, calcium-49, calcium-61, right? As a continuous function of the energy. You can see here the bound states that show up as peaks and some resonances in the continuum that show up like as narrow features, right? And in this case, we need a particular specification for the structure, and we were using the dispersive optical model for the optical potential that was developed at the University of St. Louis. Okay, there were also some friends here from the University of St. Louis that participated in that sort of application of the Green function transfer. And again, that, if you want, is a test of the reliability of that particular structure approach, which is partly phenomenological, which is the dispersive optical model, in describing the single particle structure, if you want, of the calcium isotope. Then, also an important application has to do with the so-called surrogate reaction. So here is a very interesting example of what I was saying in terms of we want to learn about what goes on when a neutron interacts with molybdenum 95, but we don't have a neutron facility, for example, or if molybdenum were not stable but were unstable, we cannot do the direct reaction. So we're going to drop the neutron on top of the molybdenum 95 by using a deuteron instead of a neutron, right? And this is an example of what I was saying before. Here, the little b, the cluster that is detected is the proton, but what we're interested in actually is the interaction between the neutron, right, the other cluster of the projectile with the target. In this case, we use a very simple description for the interaction between the neutron and the target. We actually use a phenomenological optical potential, which is the Cohen de la Roche, right? And we do the calculation. So here, we are telling the experimentalists that participated in that work, this is the probability that you have of populating a molybdenum 96, right, as a function of the excitation energy of molybdenum 96 and of the angular momentum of the residual nucleus. If you have that, you can look at the decay, right? At the gamma decay that goes after the population of that excited molybdenum 96, you can look at the gammas. Those are the experimental results. So they detected the proton and the gammas in coincidence. And if you fit, and if you fit that particular observed decay, right, with the parameters of the statistical model that decay, you can adjust them, you can fit the data, and you have everything you need now to describe what would go on in the direct reaction case, when instead of having a DP reaction, you have a neutron-induced capture. And you can compare,
Quickly ask, so what was on the y-axis? Is it the probability?
Probability. This is a probability.
Of P gamma?
This is a probability for the detection of this particular gamma once you know that the molybdenum 96 have been formed, right?
Okay.
That means, for example, that particular transition collects all the decay strength, this particular case. It's usually a little bit more complicated. So then you can use that information to try to see this was a benchmark, this was a test of the method. So in this case, we have the direct measure of the neutron capture cross-section, right? And you can close your eyes and say, okay, let's assume that we didn't know what the neutron capture cross-section was. Let's see what we will have inferred. And actually, what we see is that the inference of the neutron capture cross-section using this method actually agrees very well with the experiment, right? Now, and if you don't take into account the characteristic of the nucleus that you are populating in terms of its angular momentum, for example, you try to apply the method and it goes horribly wrong. So it's important to actually account for the reaction aspect of the process like we did. Another application, right? Let's assume that we want to learn about the structure of lithium-10. Lithium-10 doesn't exist properly, right? Lithium-10 is unbound. If you have, somebody gives you a little amount of lithium-10, in 10 to the minus 20 seconds, it just disappears because the neutron goes away, like it's unbound. So how do you study such, a system that just exists for 10 to the minus 20 seconds? You just produce it, right, with a DP reaction by throwing a neutron on top of lithium-9, right? And you expect to learn something about that very elusive system by observing the proton. So this is, again, a good test case for the GFT. I'm not going to go through, because I want to get through how the structure is calculated in this particular case. I want to make the point, right, that this Green function transfer formalism is flexible enough to account for different structure approaches. In this case, this is nuclear field theory. This is very cool, this is nice, but I don't have a lot of time. Just assume that someone who's smarter than me actually does the calculation. All the calculation, it accounts for the parity inversion, famous, which is very important. And from that calculation, one gets the optical potential which my structure colleagues here prefer to call the self-energy in this context, okay? But the important thing is that you can calculate that optical potential, that self-energy within that particular structure approach and compare, apply the GFT and compare what you get as a function of the experimental results. Here, everything is in the continuum. This zero here is the neutron emission threshold. Lithium 10 is all in the continuum anyway. Of course, the continuum, as I said before, is also interesting, right? So you have features, you have resonances, so things are going on, they have spins and have parities. And if you are able to account for them, right, you can do the experiment and compare with your theory. It works also for beryllium 11. So yesterday I saw that people are still looking at also at the DP reaction on beryllium 10 to populate beryllium 11, and we had also a paper where we also calculated within that formalism the cross section for also that resonance here. I mean, for the two bound state and that differ half resonance. Also, I think that the 3.5 minus is the one that now is interesting. So that is another application. And this, I'm essentially done, right? This is just a teaser. So I'm just going to mention some of the directions I would like to go on, so we have some time for discussion. So we want to connect, I want to go a little bit fast. So one can either calculate the optical potential, right? And do some heavy lifting, heavy structure lifting, or one can follow a different kind of philosophy, which is actually to fit it, right? To do the experiment and to fit the result in terms of positions of resonances, partial widths, and so on and so forth. This is the R matrix theory. The R matrix theory is something that works for two-body scattering, right? So what you do, essentially, as I said, you fit the observed cross-section, right? You fit the observed cross-section with, this is a little bit complicated, you have partial widths, you have energies, and you hope that at some point you fit the observed cross-section, and you can find everything you need to know of the R matrix theory in this paper, for example. But what we can do is to apply the same philosophy but to the three-body scattering. And it turns out that one can also fit, right? That the observed three-body, imagine that you do the experiment, you don't know theory, you do the experiment, you fit the result, and you can see that you can also write down the T matrix for that particular three-body process in terms of the same parameters of the two-body scattering that you will get for the R matrix, except that you have a broadening factor, but just, ask for it later. So, but the point is that you can also fit the result of the three-body scattering in terms of the parameters, right, that gives you the R matrix parameterization that are useful also for astrophysics and so on and so forth. That's an idea. Another thing is to connect another unification with the statistical description. And this is, for example, to illustrate this, and this is my last slide, we have here, again, the shell model description of magnesium 25, I told you about a little bit earlier, and we can just plot the cumulative number of levels that one finds in the spectrum, right, as a function of the excitation energy, right? So we have all those 600 states that Costas gave us, and we plot them here against the excitation energy. And we see that looks a lot like the phenomenological level density that one has, that one needs to use in a Hausdorff-Feshbach statistical description of the decay of nuclei. We also have transmission coefficients. I'm not going to go to enter here, but those are another one of the important ingredients that go into the description of the statistical decay. What do I want to highlight here is that one can gap or cross the bridge between, a structure, sort of a microscopic description of the nucleus and the statistical description, and actually use it in regions, right, in which we might not trust very well the phenomenological parameterization of level densities, gamma strength factors, and so on and so forth. Okay, and this is the final slide where I highlight one of the things that we think would be interesting to do, where we go from there. And just to have some time for discussions, I'm going just to thank you, all of you, highlight some of my collaborators, and I'm hoping I will get some questions.
Any questions? Yeah, Patrick.
Very nice talk. On the slide where you have all the different calcium isotopes,
Yeah.
You said because it's dispersive, it reproduces the positive and negative energy.
I didn't say this, but this is correct.
Sure. Can you explain the connection, like why being dispersive means that it does that?
Well, okay. It is not being dispersive doesn't guarantee you that you describe both. It just gives you the possibility of describing both, right? So the dispersivity connects the imaginary part, for example, with the real part at all energy, right? So it gives you a mathematical prescription to connect what is going on at a particular energy with what goes on at all of the other energies through the Kramer-Kronig dispersive relations. I mean, I can show you. It's actually pretty simple.
Any other questions?
On the last slide with the transmission coefficients in magnesium, were those calculated in the shell model? Or using the optical potential you
Oh,
drew?
using the optical potential. So the transmission coefficient are calculated with the optical potential. Transmission coefficients are essentially encoded absorption cross sections.
Right.
If you will. So, and the absorption cross section that I showed, right, were a function of the imaginary part of the optical potential, which in this case, the optical potential was calculated with the shell model. So that's the connection.
So does this mean that you can calculate compound nucleus contribution with it?
This is something to be explored. Yeah, I think there is hope for that. Let's say.
So I have a question. It's very varied and dense talk, but I have a question on the R matrix comments, the ones that you sort of rushed a little bit through. I'm trying to understand what the motivation was. So is the idea that you would want to be able to extract energies and widths of states from DP data instead of direct and gamma data?
Yes.
Okay.
Yes.
And it's just because it's more complex, the reaction is more complex. You can't just do Bragg-Wigner's,
You cannot do the Bragg-Wigner because you would be ignoring the interference effect between overlapping resonances, for example, right? So the parameters of the fit of the R matrix are not absolute values, are partial widths that have a phase, right? And that accounts completely for quantum effects like interferences and stuff like that. And this is what experimentalists use actually to present the results of the direct measurement and to connect with astrophysical rates and things like that. So the idea is that you can fit those with a DP or lithium-6D if you're interested in alpha-induced reaction, right? You can directly fit the cross-section and actually retrieve what would be the R matrix parameterization of the direct.
Okay, there's a question on Zoom. Phil, you can just unmute yourself and ask the question.
Hello, can you hear me?
Yep.
So I had a question about this exact thing. In fact, is it you said about the interferences? Is the interference that you get from the transfer reaction the same as the interference in the scattering reaction? Can you relate those two things? Because I don't know if the phase is the same between them. But,
If I am correct, it is. So this is work in progress. My point is that it is, right? My point is that the description of the DP reaction, if you want, of lithium-6D, if you like alpha-induced reaction, right, can be expressed in terms of exactly the same partial width and energies of the R matrix parameterization that would account for the interference effect of the direct reaction, not the DP. That's my point. There is a little broadening factor here, but okay, that accounts for the internal movement of the neutron in the deuteron or of the alpha particle in the lithium-6.
But sorry, can I follow up on that? Just because Phil's point is, I think is pertinent, particularly because you may have bound states in the other rearrangement channel, right? So
Yes.
you may have other states, there may be other poles in the other rearrangement
Okay,
channel,
you're
and those
right.
things talk to each other.
Okay.
I
so-
apologize. I was told to sound the alarm at 55 because there's a defense happening.
Okay,
here
you're
at
right,
12, and I'm
Okay.
doing that right now. I'm sounding the alarm.
That's fine.
I mean, everyone stays. There's gonna be defense.
Okay, sure. I'll be here like the whole week, so if you have questions, just come by. I'm in the theory AO, very close to Philomena and Gregor, so I'd be happy to answer whatever question you might have.
Okay, let's thank Gregory again.
To do it like